Hello, how is everyone?
Good, how are you?
Happy Monday. Is there a big difference between Monday and other days these days? Some difference in going to class, but no answer. So?
Not really. Every day it looks like pretty much the same, and it feels the same.
Yeah. For me, there is, of course, difference in days when there's teaching, there's no teaching. But other than that, there's certain similar level of activity. Okay, well, regardless of the differences, I hope your Monday so far is good. Let me share my screen. All right. I have some video processing in the background. I hope it's not gonna slow down or cause disturbances in my... Okay. Do we remember anything from last week? What are the pore throat networks? Why am I interested in pore throat networks? Do you have any recollection of what we discussed on Wednesday? So here's an example. Of pore throat networks. What is the ultimate goal? Why do I want to create a network based on my porous medium?
So we're able to simulate flow.
Right. So what is the benefit of simulating through a network of tubes? It's faster. So essentially, when I have a tube, let's look at this image. So this is just our bundle of tubes model, the one that you have seen in petrophysics a lot, and we have reviewed here. We have formulas for flux of anything through a cylindrical tube. Now, the way we put them together, when we put them into a network, we still have those formulas for fluxes, meaning I can evaluate them immediately. If you give me, for instance, for flow, if you give me the pressures at the end of the tube, and if you give me the radius of the tube and the viscosity of the fluid, I know what the flux is, and the length of the tube, of course. I know what the flux through that tube is in meter cubes per second, for instance. If I put such tubes into a network, and I can literally, I'll do that with the pencils right here. So basically, if I put those tubes in a network, I know that at steady state, whatever comes into one of these nodes, that were three, in this case, 3 tubes. Whoa, I cannot hold 3, so I'm just gonna hold 2. However many I have that come into this connection, whatever flux is coming in has to come out. So I do a mass balance on a larger scale, if you will, through these tubes, and that allows me to set up equations for flow through this network, and the flow equilibrates over the entire network. If I have some idea of what this radii should be to be representative of a porous medium, then I'm cooking. I can actually predict flow through a porous medium. So that is the whole idea behind the exercise of trying to get network set for a porous medium. Now, I'm typically speaking in terms of flow. That is often the first order of what we want to predict in porous media. Second order. First order is how much is down there. That is basically porosity and saturation. And then second order is how fast can I get it out. So that's permeability and relative permeability. Now, you could do the similar thing for heat transfer or for electrical conductivity and basically simulate resistivity. Similarly, though of course then it's going to be important to understand where the fluids are and what, because resistivity of oil and water are two different things. In any event, these concepts are helpful for understanding how porous media transport functions. So in this course, this being digital rock petrophysics, we are trying to understand how would I, given an image or some sort of description of the porous medium, how would I set up this network? Okay. All right, so last time around we did basically, there are two main lines of work in terms of the algorithms that are used underneath. One is for model or granular media. When I say model media, that means that I have a good description of individual grains in my medium. And if I have that, such as in the case of sphere packs, then I can use an algorithm called Delaunay tessellation, which is a very powerful algorithm that is used a lot in any kind of breakup of a domain into tetrahedra in 3D or triangles in 2D. So it's very important in meshing, and it kind of perseveres in a lot of areas, and is also readily available. It's available in Python, in MATLAB, you name it, in C, C++, and so forth. The second concepts are just for those general or what I call real imaged materials. That doesn't mean that we cannot image sphere packs. Of course we can, but these are more generalizable algorithms that don't necessarily understand the underlying granular nature of the medium, or possibly one doesn't exist. So we're gonna go over those algorithms. We're gonna, in terms of details, I've done a general overview of multiple algorithms last time, but we're gonna in details work with so-called watershed algorithms. They're actually some borrowing a lot from what we already know about Euclidean distance and somewhat medial axis extraction as well. And they're generally applicable in all kinds of media, and that this watershed algorithm is the one that we're going to spend the most time on, because I think it's accepted as one of the simpler algorithms to work with. Okay, so just a general idea, just to recall a general idea between for Delaunay tessellation. If I have, for instance, spherical description of the media, so I have spheres, each sphere has a center and the radius, and then I can basically in 2D form triangles. Each three closest spheres form a triangle, and I'm underlining here, and then second triangle, third triangle. That triangle is essentially my pore, and I can also look at this, so that is the network of sphere centers. And then I also realize that I have a dual network to it, and that is basically formed, so this triangle has a center right here, and then this neighboring triangle has a center right here. The line in between them is orthogonal to this line over here from Delaunay tessellation. And I actually also have, I end up with polygons that are surrounding each sphere center. And those polygons are so-called Voronoi polygons. And one characteristic of those Voronoi polygons is that the edges are basically connections of what I interpret as pores in the medium. But also these edges outline a polygon such that points in this polygon are the closest to this sphere center right here. So it's also a solution to so-called post office problems. So this is where I should place a post office if I want to all of these areas to be serviced well by that post office. So there are these two dual networks that are implemented, and again, those algorithms are available in solving a lot of problems. In 2D, this network that I get is basically each pore has 3 neighbors. Okay? So that is in 2D. There's an equivalent in 3D, where instead of triangles, I have tetrahedra. So each pore has 4 neighbors, and then I get a network that looks like this. So this describes the connectivity of my granular pore spaces in my granular medium. Okay, now we will look at we will get back to this network, well, hopefully by the end of this class, if we're working on the exercises fast enough. Now, in general images, one can go and search for throats or the tight spots in a so-called, what I call brute force search, and there's multiple algorithms for that. And then, so this is an example of such a throat. So this is my throat surface. I have in that search acquired a loop of voxels, grain voxels that are surrounding this medial axis line path. And this is something that requires medial axis as a starting point for the search. I have mentioned already that medial axis is often used that way. So essentially then I can find this polygonal surface, extract information such as area and so forth. I can also create this block of voxels that are then actually used as, I call them roadblocks or throat barriers, that enable me to figure out where my pores are. So when I place all of the roadblocks into my porous medium, here's one example extracted pore. So now you don't see any other pores, but you see transparent solid surface. You see medial axis paths within a pore, and then you see 4 so-called throat barriers at the edges of that pore. So this is, for instance, an example pore from a sandstone that has 4 neighbors. Okay, now there's various variations on the theme for these algorithms. All of them take quite a bit of a long time to process an image. So it's not fast by any shape of imagination. What's important to remember is that medial axis in itself is not equivalent to this pore throat network. So I will often have multiple medial axis centers and paths within a single pore, and that's because often, for instance, on this medial axis that is here in between, let me get here. So for instance, this medial axis that I'm seeing here, I did not find the throat. The throat really doesn't exist across here. So essentially, and for some reason, there's one not found here, or maybe it was thrown away. So this is an example pore that has multiple throats, 1, 2, 3, 4, 5, 6, 7. So this is a coordination number 7. So medial axis is not equivalent to a pore throat network. I have to go through further search to find throats and assemble pore throat network. Once I have pore throat network, I can extract various statistics. We also mentioned maximal Bowles algorithm. It's quite popular. That one processes Euclidean distances. Remember that Euclidean distance for every pixel or voxel is the distance to the closest opposite phase. So it's essentially radius of the maximum bowl I can inscribe inside pore space. So this is such a bowl or disk in 2D, and so you can see these maximum bowls inscribed into a medium. There's a way to process this recursively to basically go, and for every 2 intersecting bowls, I can figure out who is subordinate to the other based on their radii. So a smaller radius wall intersecting a larger one becomes a subordinate to the larger. And you end up with certain master balls that don't intersect. And those master balls and they're all of their subordinates basically delineate pores. And I will get, so here are two master balls at A and D. So essentially A and all of its subordinates is one pore here, and D and all of its subordinates is another pore. And I can go and find intersecting subordinates for A and D, and they're the ones that define a throat, or where the throat is, okay? So I can assemble network that way. Now we will actually go through so-called morphology-based algorithms or watershed-based pore partitioning, and that works both for finding pores as well as grains. So I will first do a little bit of history, and then I will delve into the details. So historically, first time that I know of that watershed pore partitioning was applied was in 1996 by Baldwin. And essentially, you start from so-called burn number, which is essentially Euclidean distance, labeled void space. And then you find local maxima of those burn numbers. Burn numbers is equivalent name for Euclidean distance space. And essentially, you start from those local maxima and you start growing spheres. That's similar to the grass fire algorithm we already defined. So when two grass fires or fire fronts touch, you stop. Okay? And that's essentially what's going to be a definition of throats. So this watershed that acquires certain pore space based on that procedure. Once you have acquired certain pore space and you have a number, say n voxels or pixels in that pore space, then you can find the pore radius by finding a center of mass. Okay, so this is similar to having an integral. The center of mass definition is integral, but here you have individual voxels, so you just do the sum. And basically, that's this center of mass is then your center of the pore. And you can also figure out where these blocks meet. You can figure out which pore is neighboring which other pore. And that allows you to define connections between the pores, as well as these blocks are your, where two pores meet, are basically a definition of throats. So you can find their centers and radii to basically define your pore throat network. And then you can again plot various distributions, which some of them are shown here from this paper for this particular image. You can see that, well, this is 1996, so it's a relatively low resolution image of a bunch of spheres. Okay. Now, this was later, 2005, 2006, applied to isolate grains as well. So Shepard and others have used this for a more general algorithm for sands and sandstones. And to this date, they're using a version of it. And this is a group from Australian National University. They're using a version of it for finding the network of pores. And Thompson, this is Karsten Thompson from LSU. Karsten Thompson is PhD advisor of Dr. Balhoff, by the way. So this is from his group. They actually applied similar algorithm to identify individual grains in a granular material, sand or sandstone. Okay? So this is an example grain partitioning from that work, Thompson and others. So this was, you can see the papers. Now, let's actually look a little bit into the detail. So first things first, you start from a segmented image of an object. And then you take the Euclidean distance transfer. This is a transfer. This is an exercise that we've already done. So this Euclidean distance transform, it labels every pixel with, which is what is essentially the maximum radius of the maximum ball that I can inscribe inside. So that's equivalent to the distance to the closest other phase. So in this case, let's say that if we're working in pores, it's to the closest grains. Now, the method, if you just go pixel by pixel and find the Euclidean distance, that's pretty naive, and that can work, except that it's not efficient. But there are efficient algorithms, and one that you're using in ImageJ is one of those. So you can actually do this pretty quickly. So that's not so close. So imagine that you have a phase here, imaginary golf course. So let's say that this is the phase that you're trying to process. And then these distances are basically, so you can see that the largest distance is here, largest distance is here, and they're getting smaller and smaller as you're close to the grain. So you basically get these layers of distances. So this is the closest distance. And then there is another layer of the second closest and so forth until you get to the center. So you can see this idea of starting from the, so basically this area here, the basic idea is that, okay, here I'm the furthest away from the edges, from the grains, right? So this is where I start. This is my basically pore center. Okay? And this is another one, this is another one, and so forth. So the idea of starting from the local maximum of the distance is right here. Now, why is actually the method called watershed? Let me see. Oh. By the way, Western Desert Art in Australia has sort of like similar parallel bodies that are going through the medium. So the idea is that if I start at these maxima, so here's basically a surface plot of a distance field. So if you look at these peaks, if I start rolling down those peaks, if I were water, I will go down to the edges. And basically, if I have competing rolls start from different peaks, I will basically acquire individual pores. So this is essentially like watershed basins around each point. If you were, you could also invert this, so you could look at it literally like a basin, or you could roll the balls from the peak. However you want to visualize this, it works. So the idea of doing this is to break down a rather complex object in individual components. In our case, these are individual pores, and then that enables me to set up that pore throat network. So it enables me to speed up simulation. So here's one thing to understand is that basically medial axis will go through these points where I have maxima in the Euclidean distance. It's just what medial axis does is, instead of, so if I were just retreating, medial axis makes sure that this connection between two maxima is maintained. So essentially, this medial axis connection between different paths should be close to this maxima in Euclidean distance. So this is why these concepts of both, they're all called morphology methods. These concepts of medial axis are not so far from this whole watershed transform. Now, here are the boundaries. So basically, if I started the grass fire from this center and these centers, then the boundary would be formed here. This is where two of them, two fronts merged. Same thing here. Now, something happened here. It seems that I started, or there was some merging that happened between these two, okay? So if I started from this and this center at the same time, then, or if I merge them prior to starting, then I would get this result. So this is an important point that I will have to get back to later. So here is a real example where we need to look into the problems that I have if I don't merge properly. So this is a Benheimer sandstone. This is the same sandstone that we looked at a subset of before. So now segmentation basically gives me pore space and then grain space. And here in grain space, I have this microporous grain, or is this clay, that will give me some multiple phases, but I can actually look at all of the grains as the same phase. And this is the Euclidean distance of the grain spaces. So in this case, let's say that I want to break up grains in individual grains. It's really the same concept, pores versus grains. So now what happens? I'm starting from the maxima of the Euclidean distance. That's where you see the brightest points. Local maxima, there are too many. So look at just this, which this is what I would envision would be the same grain. There are too many local maxima, and that results in problems. So if I'm actually going to start the watershed and start acquiring, this was done in 3D, so there are things that we don't see here that are coming from the bottom. But if I start from these local maxima, I will essentially get way too many grains. So things, and some of these boundaries are really unnaturally looking, okay? Or this is not how I envision grain looks like. So I have to do some of the region merging. Basically, this watershed transform by default will find a separate region for every maximum of the distance function that there is, local maximum. So one has to filter them somehow. I think by now you're realizing that in image analysis, you always have to filter something somehow. So if you have these local maxima that are barely maxima, they don't rise high enough from all the other surrounding points, then that they should be merged with their neighbors. One could try to smooth the Euclidean distance prior to watershed. Ultimately, it comes down to playing with it quite a bit, okay? And or you can, at the end, figure out the quality of these. So for instance, in here, if I look at these, well, these are low quality regions that I should try to merge together. And if that is done, this low quality region still stays the same. So I will get something like this. It's not still perfect, but on a certain level, it's also hard to tell in this particular image what the result should be. It's easier to tell in something that is more, where grains are better identified and more convex than they are in this, okay? So there are different types of filtering will give you a different result. Ultimately, you have to look at these results as statistical aggregates. Now, you can, if you partition the pore space, you get similar things. So here's the pore space, you get the Euclidean distance, and then you get all of the regions, and some merging has to be done. So for instance, focus on all of these. These should all be, I should merge some of the starting pixels before, or voxels before I actually get the region like this, okay? So let's actually try this out. Okay? So open up image J. Open up image J, and let's open one of those beads, dry slice 150. See if it's on my recent. I think. let's try this one. Oh, it's not segment. Well, I can segment it quickly. So you can either open the binary version or binarize this quickly. Let's just try making binary. Okay. And if I binarize this, let's actually start first, since these are obvious grains, let's try to start first breaking things down into grains. So I'm just gonna quickly invert this. Okay, so that I'm working with grains. So now my grains are 255. And therefore white color. Did everybody get here? So should I wait for a moment? Have my third coffee for today. Did everybody open this up before I start going further?
Yes.
Okay. So what is the major problem? If I wanted to identify individual grains in this image, my eyes say this should be easy. Here's a grain. Here's a grain. The problem is, here's a grain. The problem is that right here, and I'm really just looking at one subset, but like right now I'm just looking at 2D and imagining this is only a 2D problem. So here's a grain, here's a grain, however, they appear merged here. And I'd like to separate them. Okay. So if I wanted to individually analyze this as 2 separate, 3 separate, 4 separate particles, so I can see quite a number of them merged here. Okay. And I want to actually individually analyze these particles, I have to somehow separate them. And the whole idea of grain separation or watershed algorithm says, okay, if I run the Euclidean distance on this, then I can actually quickly do that. I'm gonna duplicate. Oops. Okay. Image duplicate. So I'm going to quickly duplicate it so I have a copy of it. So if I do Euclidean distance, if you remember, exact. Yeah, it was exact Euclidean distance, run. Okay. So you will see that basically, if I start watershed from this center and this center, this is where my local maxima of Euclidean distance are. These two will then merge somewhere here, and I will be able to separate those two grains. So if this is already implemented in 2D in the binary, versus binary watershed. There we go. There's distance map here as well. So if I do watershed, you will actually see that these particles got separated. Okay. And now that I separated this one and this one, this is a pretty good job for spherical particles. Now I can actually go and analyze this particle and this particle separately. And my particle analyzer works just fine. So what watershed in this particular case did, it basically these points where I would identify necks, where two fronts have merged, they have been converted to the opposite phase in order to separate these as two separate grains. How would I get the location of these, what I call throats or necks? Any idea?
What do you mean by location?
So if I actually just want to find out where are these necks, obviously, so here it is, right? So it's here somewhere.
Oh, I could just like subtract the images or something.
So basically you can manipulate it or compare these two to figure out where these barriers are. Right?
Yeah. Or
Which,
XOR.
if I wanted throats, that's where they would be, right? Or my necks. Or contacts. I wanted to, if the objective of my my analysis was to analyze grain network and where the grain contacts are, that is in mechanics very important, then that's how I would get those necks. Okay, so back to this image, you can then use the analyze particle analyzer, and we're just going to use it in 2D. There's multiple applications of particle analyzer. We used some of it already. Some of it is already, some of it is also in BoneJ. So let's see which one. This one has a nice coloring scheme. So I'm just going to do plugins, analyze particle analyzer. Analyze particle analyzer. Is it the same? Okay, I'm gonna search for it. This might have changed. Oh, plugins BoneJ. And you are already familiar with this. You can do anything here. I'm gonna not do the right, but here they are. So each particle that has been found is in different color, and you can look at its volume, ID, so forth. And this again is an image that you can separately analyze, download and analyze somewhere else, not necessarily just in ImageJ. So again, the coloring scheme really depends on your choice, but this one's not bad. So I will wait for a moment for everybody to try. So in 2D, this is pretty straightforward. Did everybody get this result?
Yes.
Should I wait for anyone? Gonna take that as a no. All right. So now we will actually repeat the same exercise for pores. So I'm just gonna go back to my image, original image. Well, I'll keep this one because it's nice, it's pretty. So I'm gonna invert this one back. So now my object of interest 255 or white as this white space is my pore space. So let's see what do we get with watershed of this pore space. If you want to run the distance map, you can. We have done that already. versus binary. Here we go. You can do distance map. I'm just gonna do watershed. And that watershed analysis gives me now these barriers where my pores are. And again, in this 2D image, everything seems just fine. That's pretty much how I would find pores if I was looking visually. And now with the same plugin, BoneJ, analyze, particle analyzer, I can do the same thing. I'm just gonna click off these 3D things. Still working on it. Apparently it's finished. I don't see the result. Do I have too many things open? Probably. Don't save. Let me try again. Maybe I have clicked off too many things. So I don't want 3D things. But the rest I would like, thank you. Ah, there we go. So now you can see individually colored pores. So each of these pores has different, well, volume or area in 2D. And you can also find the centroid information. So these would be your pore centers. Questions?
Could you please repeat that again about the pore center?
So here is an object right here. Do you see this red one?
Yes.
That's a pore. So I need a pore center, right? So I have identified a pore, which is great, but where's my pore center? So what this algorithm does, and that was actually here on the screen when I started talking about it, it finds a radius that is basically sum of, so this is now understood as a vector. So each point within that pore, literally each pixel in this case, has xi, yi. And you sum them all up and find and divide by the number of them, and that gives you a centroid. So x, y points of that centroid are given here. So which color is this? This is value 15. So this is my pore 15 right here. Okay.
Okay. I just wanted to make sure that those weren't like locations.
Yeah, so the location of the centroid. So that's what it means by cent. So it's really like integrate and divide.
Okay.
Get the central location. And that's how you would get for any object that it's center of mass. Yeah.
Okay, thank you.
And it's an integral. An integral is a sum in this digital world. Any other questions? Okay. And then you can get, again, enclosed volume and all of those details from there's also these moments of inertia along three axes. There should be two. Not sure what the Z one is. Moments of inertia that can tell you sort of like diameters in two different directions. if you're interested in those. Back to my presentation. My presentation is hidden here on the bottom. Here we go. Now, what I will give you. So again, I already commented on things that you can calculate for each of those regions, and that can give you statistics if you need it. And also you can assemble. So there's a little bit of work to assemble a network from those. And then here's an example. I'm not going to do this, but basically this is with image calculator, you can basically differentiate these two: original pore space image and this one done by water separation, to basically give you locations, so you can see the locations of these droughts. Then to actually assemble who is neighboring whom, you would go to this drought and look in its neighborhood to see which pores in that labeled image, which pores do I have in the label in the neighborhood, and then you would see the two neighbors that are basically that this throat is separating. In 2D, it's actually relatively straightforward. A whole lot of things are straightforward in 2D. In 3D, you might get actually three neighbors in the neighborhood, or one throat. That's a whole another issues. This is also why one should get some of the merging done. Okay, so you can then a similar thing. You can do similar thing for those grain contacts, and you can characterize grain contacts. Okay. Now, what I will, what you have as an advanced exercise is in the same. So just please verify that you can access it. If you go to the data for that I shared on Canvas, there should be a data folder, and in that data folder, there should be pore throat network advanced exercise. It's a good question. Is it there? Construct PT network. Here we go. Under data, you should have construct PT network exercise. So there is 2D and 3D exercise. And this is going to be, you guessed it, your homework. You can choose 2D or 3D. And if you want both, that'd be great. So the 2D exercise goes over, let's see if this is the image. Wow, this is on this computer poorly resolved. This photo viewer has to be, but there is actually a image of a sandstone underneath here that is just, I don't know how to manipulate in this viewer. Do you see it on my screen now? And then there is segmented image, also relatively low resolution, that you will use as an exercise. And you will go through, in 2D image, you can go through the exercise of segmenting this. And there's basically steps you need to look through. And then the watershed exercise, just like we did, but for a sandstone. And then basically analyzing the grain statistics, figure out area of each grain, also calculate something called circularity, which is what geologists often quantify. an aspect ratio of all of these fitted ellipse to each grain. And then the contact statistics. So basically differentiate image between the watershed and the original image to basically look at the grain contacts. So that's, you can then repeat the exercise for pore spaces and do the pore space analysis. So this is equivalent to what we just did in the class, but for a sandstone image. Then, if you're interested, there is a 3D problem. It's a little larger operation to analyze 3D, and it requires 3D image J suite. Okay, and I essentially provided a macro that you possibly just need to modify in your image J to basically modify where the location of the image is. Okay? And this is a kitten image. It's the same kitten or similar kitten that we looked at for those oil blobs. So kitten is a limestone, but it's granular in origin, or one can easily identify relatively ellipsoidal grains. And it's provided in the subfolder, and basically this macro has options for merging that I personally played with that you can use to actually get the watershed of the pore space. Now, and to get the pore throat network. I also provided a preprint this chapter of carbonate chapter that actually has appendix. I will open it up just to show it. And this appendix, basically there's a description of a step-by-step what needs to be done, both for a sphere pack and for both for a sphere pack and for this kitten limestone. Also, what would you do in 3D to assemble the pore throat network? Apparently, it takes a moment to apply. This is actually, now I can update, but the paper is actually published in Marine and Petroleum Geology. So again, there are step-by-step instructions to how to assemble a network. So here is an example for a larger 2D disk packing, similar thing that we've done right now here. And then also suggestion of how to do MATLAB to establish a pore throat network. And then there's this kitten carbonate example. There are some snapshots of how this, both the analysis of individual grains or individual pores would go in kitten. Okay, so that's going to be, again, I will let you do 3D if you're interested in something 3D that is more complex, but for the purpose of the exercise in this class, I'll let you pick 2D or 3D. So 2D problem with a sandstone or this 3D problem with kitten. Okay, any questions so far? No? Okay. So now I would like to get to some exercise with actual network. And for that, for simplicity, we will use the simple sphere pack network model. Okay. So I have already explained some of the networks, some of how to use Delaunay tessellation to actually get the network. I will actually now, so I will ask you to now open up. So everybody said that you do have MATLAB. So if you can open up MATLAB on your computer. I was reinstalling MATLAB, so hopefully it has. Oh, I'm still installing. I had to reinstall on my computer and I wanted to install the new version. So apparently I don't have it running. I'm still working on it, but you can run on your own. I'm just gonna open and explain. So everybody please open MATLAB. So in essence, if I had a pore throat network, and here there is some, there is basically results for sphere packings that are available as text files. This was done using a separate code. So these are simply results of a number of sphere packings. And those text files, I can open one, they actually have the number of spheres, and then for every sphere, they have X, Y, Z coordinate, radius, and some other information. But this basically first 4 columns define a sphere packing. And this is the information that is imported to MATLAB as the starting point information. Now this sphere packing software is software that I have inherited after working with Dr. Bryant. It's actually implementation of so-called cooperative sphere packing. And the result is relative to a box that is always of size 70. So when you ask to pack 20 spheres, then they will be larger. The radii here are 14 within that box of 70. Now, if you open a different packing, let's say where you ask to do 200 grains, then the radii will be smaller. So again, these radii are always just trying to fill in a box that is 70 cube. So they should always be just normalized if you're interested in anything and multiply it with whatever. And this is what also this number 70 in the formula is. Now, the MATLAB has implementation of Delaunay tessellation. So basically you can get for any sphere packing or any set of X, Y, Z coordinates, you can get Delaunay tessellation. The result of this Delaunay tessellation, for instance, in this particular case, is really, so if you give it numbered sequence or a sequence of spheres in certain order, then the result will be tessellation, say T, and that tessellation is basically just labels of spheres that are center of a tetrahedron. So there will be a set of 4 tuples of numbers. So each 4 tuple defines vertices of tetrahedron, and each tetrahedron defines a pore. So essentially any tessellation software in anything can give you the sets of these tetrahedra that is the starting point for tessellation. So again, remember in 3D, I have this tetrahedra that are equivalents of what was in 2D a triangle. Okay. So great, so those are basically, you get this is a box of initial spheres, then you get these tetrahedra that are defined by 4 tuplets of spheres, and then each tetrahedron you process to get pore, and you also know which pores are neighboring which other pore. Okay, so that's essential procedure in getting a pore throat network. And since it's relatively simple and quickly available in a lot of software, this is why this is the starting point of the exercise. So once I have these pore throats. I can also process them to get what the inscribed radii of each throat is. And then I will set fluxes through each of the throat, Qij. And if you remember, I have the radius Ij in that is defining this throat or this. Yes? Questions? No? Okay. So this radius defines the flux through the throat. So when I assemble the network, I basically have to assume that I have a steady state, and all of the things coming in have to also leave my every pore. So for every pore, I go around the neighboring pores and set up the equations for pressures. And this was the little example, or very simple example, that we've done as a quiz in class. So when you assemble this network, you can then set up the equations, find these pressures as a solution to the system of linear equations. And once you do, then you can figure out what's coming through out on one of the boundaries and compare that to Darcy's law to find permeability. Okay? So this code network flow calculation is available to you. So if you can find, I'm just gonna open this since my MATLAB is still installing or reinstalling. And I apparently didn't start it early enough, probably because I'm also processing a video file from the previous class, so that together is too much. Open with, let's just do maps. Just give me Notepad. Okay. So you can import, for an example network, you can import these results, which is basically a sphere packing. The box is always 70 cube. X, Y, Z's, and R's are basically given by this imported data. So those are first, second, third, and fourth column. And there's a prepare network. Let me open. This prepare network function basically extracts this Delaunay tessellation. What it does, this packing of spheres is periodic, so it replicates it replicates it on each sides, and then it finds the Delaunay tessellation and uses information only from the center box. Okay, and you can, this prepare network, you can also, this is Delaunay n is the function that runs Delaunay tessellation. And the result, so basically this tessellation 0 will be actually set of these tetrahedra. And then basically you process the set of these tetrahedra to find information on the network, okay? So after you complete the tessellation, you can find and figure out the neighborhood relationships between these tetrahedra. Okay. How do you find the two tetrahedra are neighboring each other? Essentially, if one tetrahedron has spheres, spheres 1, 2, 3, 4, and the other one 3, 4, 2, 3, 4, 5, then 2, 3, 4 is the side or throat that is shared between those two, and that is your throat neighboring to tetrahedra. Therefore, that's a throat neighboring two pores. So you can analyze those tetrahedra to get the information, and that's done in this prepared network. Now, you can also view. So can you run view modify packing or view packing just to see it? Then the network flow calculation runs these calculations that I basically have outlined on this file, or on this slide. Can everybody verify that you can run it? And you can view this packing. It's good to view smaller packing. So what I want you to do in this exercise, and basically in the remaining time that should be enough, is to run such as this example. You can view small packing just to get the feeling for it. Apologies for my MATLAB not being running. And then you can run example network and modify this example network to run for 100, 200, 500, and 1,000 spheres that are in these files, appropriately named files. So I want you to run it and get the permeability. And find permeability. So perm is the permeability. You also need porosity. And that is done with porosity estimate function. So this exercise 2 please assimilate like permeability versus grain radius, permeability versus porosity, and normalize permeability divided by R squared versus porosity. So again, this is just elaboration of what it does. These are the 3 key files in that exercise. And I have it in run example network, how they're called. So I want you to run this exercise now and basically have it ready, these results for next time. And then we can discuss them. So I can end this class a little early. You can all work on running these. And just please have them ready for next Wednesday. And then that's going to be the starting point of our next discussion. Any questions? Everybody's, I hope, silently working on these. All right. So please finish this exercise 2 and have these results for different packings ready, and then we will talk about them next time. But this should kind of give you a basic idea of how network models work and how does one, for instance, get permeability from them. And This code is from Dr. Bryant. So if you do ever use it, also cite his papers. Okay. All right.
Okay.
Well, I see you virtually on Wednesday. Did everybody get my comments about the projects?
Yes.
If you have any questions, please let me know, or if you need to separately meet to discuss. Okay. All right. I see you on Wednesday.